Thanks, Alex. So today what I'm going to present, really, it's not results. We're not there yet. We've only just got the core back in Adelaide, so I'm not going to present a lot on results, but I'm going to present more about the workflow that we did and the whys and the hows of this drilling program and all of this, the additional data collection and synthesis that we've done on top of just the drilling. So it's really important that I acknowledge that this is a collaborative effort. There's been multiple data acquisition programs within this. We've had multiple sponsors funding parts of that, and it's really important, I think, that I acknowledge Geoscience Australia. They've contributed a lot in this in terms of financial support, but also ongoing research collaboration. But it's important to note that there's a lot of people involved in this work, including our fellow surveyor from across the border and a bunch of universities. So I guess the first question is, why is it important that a state geological survey actually goes out into these remote, underexplored regions? What is our purpose in doing that? And I think Steve touched on it early on. I think there's a number of reasons. One of those is I think there's a fundamental role in geological surveys going into these sort of frontier areas, these regions undercover where there's little known, and actually taking some of the risk, building a framework and providing something for explorers to base their models on, so de-risking areas for exploration. In a place like the Coompana province, it's also important because this area is actually covered by national parks. So it provides a good opportunity for us to work closely with other government departments, such as the Environment Department, to actually develop an appropriate way to work in these areas. And as you can see from this map, the Coompana province in the far west of South Australia is a big chunk of South Australia. And it's not only that, it's a big chunk of Australia. So it really is vitally important that actually we do understand something about this large piece of Australia and how this fits in with surrounding cratonic blocks such as the Musgrave province, the Gawler, how it interacts with the Yilgarn in the west. And I think it's also really important that we understand cratonic margins. We saw just then in Sandy's talk, many of these mineral systems that we know of, they're developed in areas where you have lithospheric style structures and on cratonic margins. So we know their perspective in their own right. If you look at the eastern margin of the Yilgarn, for example, we know there are mineral deposits there. These areas are highly prospective. But it's also really important because the tectonic setting, the tectonic drivers that are occurring on these continental margins have a key role in what's going on behind them within the continent itself. And so it can actually give us insights into the mineral systems developing within the Craton as well. So these are things like the Olympic Dam, the 1600 mineral systems within the Gawler. So the Coompana really is an unexplored frontier. It's a huge area, about 200,000 square kilometres for the whole province, and there is not a single exposed basement rock. So we have no idea what the basement is. There's been very limited mineral exploration, probably because of that fear of cover. The last exploration drill hole in South Australia was back in 1982. So this really is one of the least understood Proterozoic terrains in Australia, and because of that, we really don't know what the mineral potential of the area probably is. So what did we know before about 2013 when we sort of embarked on this? Well, not a lot. So we had, as I said, we had no outcrop, very limited drill holes, and we also had very poor resolution data, so very poor magnetic data. We're talking here 1 and 2 mile spaced magnetics, no radiometrics, gravity between 7 and 15 kilometres. So not enough for us to actually be able to map anything, to be able to understand what's going on, but enough to give us a bit of a hint. You know, we knew that there were very interesting features, things like this remnantly magnetised Coompana magnetic anomaly, this big feature that it's enigmatic. What is it? We knew it was there, but we didn't know anything about it. We did have a few drill holes out there. These were these early exploration wells. There were 3 diamond drill holes on the South Australian side that intersected the basement. The first one was a petroleum well, Malaby 1, that intersected what was dated a 1,500 million year old orthogneiss, felsic orthogneiss, at about 1,400 metres depth. 2 other holes were drilled over the Coompana anomaly, and both of these intersected mafic volcanics and intrusives of unknown affinity. We didn't know where they fit. Importantly, there are also a couple of percussion holes out there, and I want to point out actually that some of these percussion wells, the Albala Karoo and Guinea Bore, these were actually drilled by the government back in the 1890s, 1892, and we still have sample of this in our core library. So we've actually managed, that bag of dust up there, we've actually managed to get a date out of this from a drill hole from the 1890s. This shows the value of having a state-run core library. In 2013, 2014, the West Australians did us a big favour and they went out there and drilled a few holes as well on the West Australian side of the border. And that's really important because that's given us a bit of a framework, it's given us some ideas to test, and it's given us the ability to say, well, what have we got on our side? So they got a couple of holes here that intersected a 1,600 million year old protolith. This is the Tylkowski supersuite, geochemical signature related to subduction modified crust. And these are temporally and chemically related, we think, to the Eastern Musgrave province and the St Peter's suite. Further west, there's this 1,500 million year Underwidgie supersuite. These are orthogneisses with magmatic characteristics of a rift-related system, similar to what we see in Malaby 1. And then across the region, we get this evidence for the Moondini supersuite. So this is related to massive A-type magmatism, significant high-temperature metamorphism, and this is this Maralinga event, which we see in the Musgrave province for the Musgravian orogeny and the Pitjantjatjara supersuite, and also in the Albany-Fraser, the Stage 2 Albany-Fraser and the Esperance supersuite. So this is a really wide-scale event. So we had a bit of an idea, and that gave us some things to test. And we sat down and thought, what are the key data sets that we want to collect that's actually going to allow some sort of framework for discovery, be that scientific discovery or exploration discovery? And so we wanted to know something about the depth and nature of the cover, the structural framework and the fluid pathways, the crustal architecture, mapping basement undercover, just what rocks are actually there. And more importantly, I think, is in what setting did those rocks form? And as Sandy said, this is a key thing, because if we know this here is it's a stylised picture for a gold system within a subduction setting, and you can see you get different styles of deposits developing in different parts of the system. So if we can map in space and time where we are within this sort of system, that gives us an idea of the types of models we want to apply and the types of exploration strategies you might want to use. So we went out there and we started collecting a lot of data. We collected things like the new crustal scale seismic line, the Coompana magnetic and radiometrics, 400 and 200 metre magnetic data across the entire area. AusLAMP, so we've got finished AusLAMP collection over the entire region. And the regional gravity, so we've infilled gravity over here from 7 kilometres or whatever it was down to 1 kilometre and 500 metre. So this is fantastic. This now gives us a picture that we can base some ideas on. We can come up with some ideas, but at the end of the day, this does just tell us something about the petrophysics of the rocks. It doesn't tell us how they formed. And so there's still a lot of questions, What is the provenance of the crust? We see the change in the crust across major structures in the seismic from a 2-layer to a 3-layer crust. What is the magnetic anomaly? Can we test those links, those proposed links between the Musgrave province and the St Peter's suite and the Coompana? And what is the age and distribution and nature of that cover? And the only way we can test that is to go and drill some holes. So we did that. This program was not about testing specific targets or anomalies. This was about drilling regions to understand the entire area. So we selected targets based on regional geophysical character. So this is answering questions like, what is the nature of this 2-layered versus 3-layered crust? We picked high magnetic zones, low magnetic zones, remnantly magnetised domains, high density structures, low density domains, areas where we know there's major structures and where we have a fabric. So from this, we identified 4 main geophysical domains and a number of structures and younger intrusions. We selected and cleared 19 drill sites, and we had 8 priority holes which would intersect each one of these different domains. An important part of this really was our engagement early on with both national parks and the Environment Department, and also the Far West Coast Aboriginal Corporation and the Advisory Committee, traditional owners. And we've had very good engagement with both the traditional owners and with Parks and Wildlife, and that has given us the ability to go out there in confidence to know that they're on board with what we're doing and they understand the reasons why we're doing it, and it's given us a really good sense of actually this is something that's important, and we've expressed to them about why this is important, these big scientific goals that we're looking at here. And of course the local community, we've had a lot of work with Border Village in particular, because they've been very, very helpful, particularly around water. So once we had our approvals in place, we then decided to go and test some of these ideas about the cover. So we ran with Sarlae and also with Geoscience Australia. We've done a bunch of test case geophysics on the cover. So we've done a bunch of magnetic modelling, depth of basement modelling, passive seismic and ANT. This was really about knowing how thick that cover is. And then we also did reflection seismic and microgravity, and this was more about understanding something about that cover. And this turned out to be very, very important. In an area like Nullarbor, where we know we have big cave systems and karst, we really didn't want to drill one of those. We didn't want to lose a drill rig down one. And we've actually, the microgravity in particular, has been very helpful in allowing us to pick areas that may be low density, therefore there might be a cavity, and you can see this here in the gravity on the left, and also in the seismic, a slow velocity zone on the right. This may have been a cave, and so we have actually moved collars based on this information, and we didn't drill a big cavity. Across the basement, the results suggested we've got a thickness of cover between sort of about 250 up to about 550 metres, and the point of this is actually the data sets that we collected worked. They gave us a lot of confidence in, and they're reasonably accurate as to the depth of cover and the nature of that cover, and they were very important actually in allowing us to plan our drill holes. This is a very challenging area to drill. We've spent a lot of time with the drillers, so Bort Longyear were contracted to drill this. We sat down with them, and it was about developing a borehole plan that would actually allow us to drill through hard cavernous limestone and then soft sediments with soiling clays, unconsolidated shales, in an area that's environmentally important, especially some of the cave systems, and preserving water, which is a rare commodity out there. So we came up with a plan to run a two-stage precrawler. So this is an example of the precrawler rig that we used. We ran an initial precrawler running air methods through the limestone, cased the limestone, then ran mud rotary through the shales, so we hot seeded down to basement. And then, this is just a video to show, and then we ran HQ3 diamond tail, so between 1 and 300 metres of diamond tails. And I think an important thing here to note too is that it's too hard to dig sumps, plus it's environmentally damaging, so we didn't want to do that. So all of this was done sumpless, using SRUs and above ground tanks. I think this gives a bit of a scope of the scale of the whole region. We also tested a lot of new technology, and part of this was with the particularly downhole methods. So we managed to talk Global Tech into testing their TrueProbe gamma spectrometer, both wireline and autonomously, to give us that extra layer of data, but also to test this new technology. We ran a trial with Bort's TrueScan. This is a field-based portable XRF core scanning equipment, which gave some really useful information, and it survived the tracks out there, which is a real testament. And we also ran downhole temperature logs as well, so give us some sort of idea of the thermal nature of the crusts in here, which we don't actually have any constraints on now. So at the end of the day, we got 8 holes drilled. We started on the 4th of April, we finished on the 11th of September. All of our holes reached basement. All of ours, we intersected each of those domains that we hoped to intersect. A total of about 4.5 kilometres of drilling for about 1,800 metres of core. And importantly, we didn't lose a hole. We didn't lose a drill string, and we didn't have any major environmental incidents. So where to now? This is, as I said, we're early days. We've got the core back. We've actually now run through, with the core in the core library, we've had a second pass log. We have run through, we've high logged all the core. We've run it through the Mineralise XRF scanner. We've taken some initial samples that we've sent off, 12 samples for geochronology, a bunch of indicative samples for geochemistry. And we've also done some structural logging. These are all oriented holes, and so we've used the Reflex IQ logger to actually take structural readings to get some sort of handle on what's going on in the structure out here. But we've still got a long way to go. But where can we take it now? So what can we actually do? Well, we can now take those geophysical images and we can put a point of truth on those, and we can actually assign a rock to that. So this is a first pass basement lithology interp map that Tom has done, based on the drilling. So you can see here that there's a number of, we can now actually map out the rocks here. I'm going to go through this very, very quickly because we actually have all of the core, or samples of all of the core out here in the thing, and Tom, Mark and Liz are going to run you through that at lunchtime. Actually, Mark and Liz, not Tom. But just to give you a bit of a flavour, what we got. So holes 1 and 4, so both holes 1 and 4 intersected deformed and migmatic bimodal orthogneisses. Within that, there was a number of locally derived undetected melts, so these have seen a fairly high-grade metamorphism, and there's also granitic sheets. These granite sheets are probably related to what we saw in holes 3 and 5. So these are these big, strongly magnetic things that look like plutons. Well, they are plutons. These are big porphyritic megacrystic granites. And within those, we actually see late cross-cutting undeformed dolerite dikes. And these are probably related to things that we see in these remnant bodies, so these dense, remnantly magnetised bodies, which when we drilled were gabbros and dolerites. Hole 6 was one that we put into one of these major structures, and this actually looks like deformed basement gneiss. But as you can see here, this has been a long-lived conduit of fluid flow. There's been a lot of fluid through this rock, which has significantly altered it from its original protolith. And the final hole we intersected, we actually drilled a bit more basement. This was the deepest hole, a bit more basin, sorry, intersecting silts and shales and these red bed sandstones, which we don't actually know where they sit in the stratigraphy. And then underneath that, mafic volcanics, similar to what we saw in some of the early exploration holes. So I think by undertaking a consistent workflow here from gap analysis to big scale data acquisition and then synthesis, we're taking an area that we had effectively no knowledge of before, and we're actually probably driving what I think is going to be the biggest step change in our knowledge of an area, definitely in my time. And this is really going to allow us to provide a framework to understand the mineral potential here, but not just here, but also to understand the tectonic drivers and tectonic setting which may be affecting the mineral systems even within places like the Gawlerkrat and the Musgrave province. And so we hope to release more results, actual results, at a day associated with the SAREC conference in May. So stay tuned, come along to that, and hopefully we'll have a bit more there. There is some data available now. These are all on your stick, so there's a whole bunch of reports. All the geophysical data is available, and there will be a lot more coming. Thank you.